The night sky might not be a window but a giant cosmic screen. This is the heart of the holographic principle, a radical idea from the edge of physics suggesting everything you see, touch, and experience in 3 dimensions could be a perfect projection from a 2-dimensional surface. By the end of this journey, you will understand how this theory could completely rewrite the rules of reality, from the nature of gravity to the fabric of space itself. We will explore how black holes force this idea into existence and whether the stars above are just pixels in the ultimate display. What feels most real to you about the world around you? To grasp this projection, we must first understand the projector. The holographic principle was not born in the study of distant galaxies, but in the terrifying depths of a black hole. It began with a paradox. Stephen Hawking made a startling calculation that shook physics to its core. He showed that black holes are not truly black. Due to quantum effects at their very edge, they slowly evaporate, emitting a faint glow we now call Hawking radiation. This was a monumental discovery, but it created a catastrophic puzzle known as the information paradox. According to quantum law, information can never be destroyed. Every bit of data about what falls into a black hole, the atoms of a star, the pages of a book, must be preserved somewhere in the universe. Yet Hawking's math suggested that as the black hole evaporates and finally vanishes, all that information vanishes with it, erased forever. This was a direct contradiction, a sign that our understanding of gravity and quantum theory was fundamentally broken. The solution came from looking at the black hole's surface, its event horizon, the point of no return. Physicists Jacob Bekenstein and Stephen Hawking had earlier found that a black hole's entropy, its measure of disorder or hidden information, is not proportional to its volume but to the area of its horizon. This was a profound clue. In our normal world, entropy grows with volume. A messy room holds more disorder than a messy drawer. But for a black hole, all the information about everything it has ever consumed seems to be painted onto its 2-dimensional spherical surface. Inspired by this, physicists Gerard T. Hooft and Leonard Susskind proposed a radical fix to the information paradox. They suggested that the information is not lost inside the hole. Instead, it is perfectly encoded pixel by pixel on the event horizon itself, like a holographic film. When the black hole radiates, it is not destroying data, it is slowly reading out that stored information back into the universe. The 3-dimensional interior of the black hole, with all its contents, is a projection from the 2-dimensional data on its skin. This was the seed. If a black hole, the most extreme object in creation, is fundamentally a hologram, then could the same principle apply to the entire cosmos? That idea of a black hole as a cosmic projector was a brilliant fix for a paradox, but it begged a much larger question. Could this be a universal law? The answer arrived in a thunderclap of mathematical elegance in 1997, when physicist Juan Maldacena proposed a concrete, breathtakingly precise model. It is called the anti-de Sitter conformal field theory correspondence, or AD-SCFT for short. This mouthful of a name describes perhaps the most profound duality ever conceived in physics. In its simplest form, the AD-SCFT correspondence states that a universe with gravity, a strange warped space with 5 dimensions, is mathematically and completely equivalent to a quantum theory of particles without any gravity at all, living on its 4-dimensional boundary. Think of it like the hologram on your credit card. The shimmering, 3-dimensional eagle you see is not really there in the plastic. It is a perfect projection from a flat, 2-dimensional film etched with microscopic patterns. In Maldacena's model, our familiar reality of 3-dimensional space plus time, with all its stars, planets, and the force of gravity weaving it together, is that projected eagle. And the true, fundamental description of everything is written on a distant, lower-dimensional surface where gravity does not exist, only quantum particles interacting. This was the cornerstone. It transformed the holographic principle from a clever idea about black holes into a full-fledged, mathematically rigorous framework that physicists could actually use. Suddenly, impossibly difficult calculations about gravity in the bulk universe could be solved by doing simpler, gravity-free calculations on its boundary, and vice versa. It was a revelation suggesting that gravity itself might not be a fundamental force, but an emergent phenomenon, a side effect of quantum information processing on the edge of reality. So if the holographic principle is true, what does that make our universe and us within it? Complete equivalence is the key that unlocks everything. This is not a rough comparison or a helpful analogy. In the mathematics of the AD-SCFT correspondence, every single event in the five-dimensional gravity-filled universe is exactly mirrored, one-to-one, by the interactions of quantum particles on its four-dimensional boundary. There are no exceptions. A star collapsing in the bulk is a specific, complex dance of quantum data on the screen. A ray of light bending around a massive object is a precise calculation performed in the quantum theory. They are two utterly different languages describing the exact same reality, like translating a novel from English into Mandarin. The story, the characters, the plot twists all remain intact, only the symbols change. This absolute duality solves the black hole information paradox with elegant finality. When matter falls into a black hole, its information is not destroyed. It is flawlessly translated and encoded onto the event horizon, which acts as a part of that fundamental boundary. The three-dimensional interior we picture, with all its crushing density, is simply how that encoded information manifests from our perspective within the projection. The evaporation via Hawking radiation is just that boundary system slowly processing and releasing the data back out. Nothing is ever lost, it only changes form. This leads to the staggering implication for our own cosmos. If gravity and the three-dimensional world can emerge from a quantum system on a lower dimensional surface, then everything we consider fundamental, the very stage of space and time, might be secondary. Imagine the heat from a cup of coffee. The warmth you feel is real, but it is not a fundamental substance. It emerges from the frantic jostling of countless invisible molecules. In the holographic view, gravity and the geometry of the universe could be like that heat, a collective illusion arising from the quantum bits of information painted on the cosmological horizon far beyond the galaxies. We are not living in the primary reality, we are living in the projection, a shadow play of unimaginable complexity happening somewhere else. This elegant mathematical duality presents a profound challenge when we look up at our own night sky. The universe described by Maldacena's model, that perfect hologram, is not our universe. It exists in a hypothetical space called anti-de Sitter space, a cosmos with a geometry of negative curvature, like the interior of a saddle. Our real universe, according to all our best measurements from telescopes like Hubble and James Webb, is not shaped like that. It is remarkably flat and, crucially, it is expanding at an accelerating rate driven by the mysterious force we call dark energy. The mathematical shape that best fits this reality is called de Sitter space, a cosmos with a positive curvature. This is the great divide, the de Sitter challenge. The stunning holographic principle has been proven to work with mathematical precision in a universe that is the geometric opposite of our own. So, the million-dollar question remains, is our universe a hologram? The honest answer is we do not yet have the proof. Finding a precise de Sitter conformal field theory correspondence, a DSCFT for our actual cosmos, is one of the most significant and difficult unsolved problems in all of theoretical physics. The core issue is that de Sitter space is fundamentally more complex and unstable for such a clean duality. In the anti-de Sitter model, the boundary of the universe is far away but static and accessible in the equations. In our expanding de Sitter universe, the cosmological horizon, the ultimate boundary from which light will never reach us, is constantly changing, receding as the universe accelerates. Trying to pin down a stable, lower-dimensional quantum system on that moving edge to project our entire reality is a problem of staggering difficulty. This creates a powerful tension in modern physics. The holographic idea is too beautiful, too powerful at solving deep paradoxes to be just a mathematical curiosity for an imaginary universe. Many physicists feel in their bones that it must apply to reality, that it is pointing toward a fundamental truth about how information, space, and gravity are woven together. Yet the bridge from the elegant world of anti-de Sitter space to our own de Sitter reality remains unbuilt. It is the thrilling frontier. So while we cannot yet say definitively that the sky is a projection, the very fact that the principle works so perfectly for a simpler cosmos suggests we are on the right path, staring at a shadow on the cave wall and beginning to suspect the existence of the fire. This unbuilt bridge to our own universe does not stop the holographic principle from making startling predictions. One of the most profound is that reality might have a resolution limit. If the three-dimensional world is a projection from a two-dimensional surface, then the information that creates it is not infinite. It is stored in discrete, fundamental units like the pixels on a screen. This leads to a startling idea: the cosmos could be pixelated. The clue to this graininess lies in the smallest possible measurement in nature, the Planck length. This is an unimaginably tiny scale, about 1.6 times 10 to the negative 35 meters. To put that in perspective, if you enlarged a single atom to the size of the observable universe, a Planck length would be roughly the height of an average tree. At this scale, our classical notions of smooth, continuous space and time are believed to break down, consumed by a violent quantum foam. The holographic principle gives this a precise meaning. It suggests that the total amount of information needed to describe any region of space is not proportional to its volume, but to the area of its surface. Think of a digital photograph on your computer. The detail in the image is not determined by how thick the file is, but by the number of pixels across its two-dimensional surface. In a holographic cosmos, every volume of space is like that photograph. Its entire three-dimensional content, every particle, every force, every ripple of gravity, is encoded on its surrounding boundary. And because that boundary has a finite area, it can only hold a finite number of information bits, one bit of information for every 4 Planck areas. This means there is a maximum amount of detail that can fit inside any given region of space. You cannot zoom in forever on a smooth continuum. Eventually, you would hit the graininess of reality, the individual pixels of spacetime itself. This challenges everything we intuitively believe. We picture space as an infinitely divisible emptiness, a stage upon which events play out. But if the holographic view is correct, space is not the stage, it is part of the performance, an emergent property of quantum data. Its smoothness is an illusion of scale, much like a television picture looks continuous from your couch, but up close it dissolves into distinct dots of colored light. The universe may not be an analog film, but a cosmic digital display running on a processor of unimaginable complexity at the edge of everything we know. This pixelated view of reality leads us to a remarkable question. Where in our universe could that fundamental two-dimensional screen actually be? Some physicists point to the very edge of the observable cosmos, to the oldest light in existence. The cosmic microwave background is the faint, cold glow that fills every direction of space. It is the afterglow of the Big Bang itself, released when the universe was a mere 380,000 years old, finally cool enough for light to travel freely. This radiation has traveled for over 13 billion years to reach our telescopes, and it carries an imprint of the universe in its infancy. For scientists exploring the holographic principle, this ancient wall of light presents a tantalizing possibility. Could the CMB itself be a kind of projection screen? Its subtle temperature variations a frozen hologram of the universe's quantum origins. The idea is that the patterns we see in this background radiation, the hot and cold spots that seeded all future galaxies, might not be random quantum fluctuations from within our three-dimensional space. Instead, they could be a direct translation of quantum information encoded on a two-dimensional surface at the boundary of the early universe. It is a staggering thought that the blueprint for everything from galaxy clusters to human beings might be painted on this primordial canvas. Researchers have searched for a specific kind of signature within the CMB's complex data. In a smooth, classical universe, the temperature fluctuations should follow certain predictable statistical patterns. But if space has a fundamental graininess, if it is built from discrete informational pixels as the holographic principle suggests, then those patterns should be subtly altered. There should be a limit to how finely detailed the fluctuations can be, a faint statistical anomaly or a preferred direction that betrays the underlying pixel grid. A few years ago, a team of scientists made headlines by analyzing data from the European Space Agency's Planck satellite. They claimed to have found just such a statistical signature, one that seemed to fit a holographic model better than the standard model of smooth inflation. It was a controversial claim, and most cosmologists remain deeply skeptical, noting the signal is faint and could be due to other effects or even instrumental noise. This is the critical point. No one is declaring proof, but this is how profound theoretical ideas are stress-tested against reality. Scientists are taking an abstract concept born from black hole paradoxes and asking a direct observational question of the cosmos. Can we see the pixels in the universe's oldest photograph? The search continues with more precise data and more refined models. Whether the CMB holds the key or not, the very attempt transforms the holographic principle from a beautiful mathematical speculation into a tangible scientific quest. We are no longer just imagining a projected sky, we are pointing our most powerful instruments at it, listening for the static of creation itself, trying to hear if it whispers in bits and bytes. Gravity feels like the most fundamental force in the universe, the great architect that sculpts galaxies and pins our feet to the ground. Yet the holographic principle suggests this might be the grandest illusion of all. Gravity and the very stage of spacetime it warps could be emergent phenomena, side effects of something deeper. To understand emergence, think about a bustling city seen from an airplane window. The traffic flows, the neighborhoods pulse with life, the entire metropolis seems to have its own rules and rhythms. But if you zoom in, you see that this complex system emerges from the simple decisions of millions of individuals, each one just going to work, heading home, or meeting a friend. The city is real, but it is not a fundamental entity, it is a collective consequence. In physics, temperature is a perfect example. When you touch a warm mug, you feel a distinct property, heat. But that warmth is not an ingredient added to the coffee. It emerges from the frantic, invisible kinetic energy of countless water molecules jostling against each other. The mug does not contain heat, it contains molecules in motion, and our experience of temperature is how we perceive that hidden dance. The holographic principle applies this same logic to the cosmos itself. In the mathematics of the duality, the three-dimensional universe with its gravitational pull is not the primary reality. It is the emergent consequence, the collective behavior, of a vast number of quantum particles interacting on a distant, lower-dimensional boundary where gravity does not even exist. Those boundary particles, governed by their own quantum rules, are like the individual citizens or the jostling molecules. Their collective state, their entangled information, projects upward to create the illusion of a continuous curved spacetime and the force we call gravity within it. A helpful, if simplified, analogy is a modern video game. You explore a breathtaking, three-dimensional world with mountains, rivers, and realistic physics. Objects fall, light casts shadows, and characters move with weight. Yet all of this rich, immersive reality emerges from lines of two-dimensional code running on your computer's processor. There is no literal gravity in the silicon chip, no actual space inside the circuitry. The game world is a projected reality, a consequence of the information being processed. In the holographic cosmos, we are inside that game. The force that holds planets in orbit and makes stars shine is not a fundamental ingredient of the universe. It is the cosmic equivalent of a physics engine, a stunningly realistic effect generated by the quantum processing happening on the boundary. This completely flips our intuition. We have always thought of spacetime as the container, the fixed stage upon which the drama of particles and forces plays out. The holographic view turns that on its head. The stage itself is part of the show, a dynamic, evolving projection that only exists because of the underlying quantum script. If this is true, then every time you drop a pen or watch the moon rise, you are not witnessing a fundamental force of nature. You are observing a shadow, a magnificent and convincing illusion generated by a deeper, stranger reality operating on a surface we may never see. That idea of a limited resolution forces us to ask a practical question about our cosmic projection. How much data can it actually hold? In our everyday experience, information scales with volume. A bigger library holds more books, a larger hard drive stores more files. The capacity grows with the three-dimensional space it occupies. This seems so obvious we rarely question it, but the holographic principle shatters this intuition, replacing it with a rule so counterintuitive it feels like a glitch in reality. This is the Bekenstein bound, named for physicist Jacob Bekenstein, who first glimpsed it in the context of black holes. The law is stark and simple. The maximum amount of information, the total number of bits needed to perfectly describe everything inside any region of space, is not proportional to the volume of that region. It is proportional to the area of its surface. Think of a sphere. In a normal three-dimensional world, the data you could pack inside grows rapidly with the cube of its radius. But in a holographic universe, the data limit grows only with the square of the radius with the size of the sphere's skin. This area law is a cornerstone prediction, a direct fingerprint of a projected reality. To feel how radical this is, picture a 1 terabyte hard drive sitting on your desk. In our conventional view, that drive's storage is defined by its three-dimensional interior, the density of its magnetic platters. In a holographic cosmos, its true information capacity would not be determined by the volume of the device in your hand. Instead, it would be dictated by the surface area of the smallest sphere you could draw around it. That sphere's surface holds the fundamental data from which the drive, its contents, and even the space it occupies are projected. The shocking implication is that a 1 terabyte drive in a holographic universe would, in a fundamental sense, be holding vastly less information than we think it does. Most of the apparent complexity inside it would be an illusion, a kind of informational mirage generated by a much simpler code written on its boundary. The universe itself operates under this severe data compression. Every star in every galaxy, every particle in every cell of your body, all of it is described by information painted on the cosmological horizon. The breathtaking three-dimensional richness we experience is not stored in 3 dimensions. It is a magnificent, real-time rendering from a 2-dimensional source. This bound tells us the cosmos is not infinitely detailed. It has a finite data plan, and the bill is paid not by cubic light-years, but by the square light-years of its ultimate surface. This finite cosmic data plan creates a paradox so severe it could tear an astronaut apart. The holographic principle, for all its elegance, has ignited a fierce debate at the very edge of a black hole, a puzzle known as the firewall paradox. It begins with a simple, horrifying scenario. Imagine you are falling toward a stellar mass black hole. According to Einstein's general relativity, this journey should be uneventful, at least initially. The event horizon is not a physical wall, it is just a point of no return in space. In a principle called the equivalence principle, you should cross it smoothly, feeling no sudden jolt, a concept physicists call no drama. But quantum mechanics, combined with the holographic view, suggests something far more violent might happen. The paradox, named for its authors Olmary, Marolf, Pulczynski, and Sully, asks a devastating question. If the information about everything that falls into a black hole is perfectly preserved on its horizon, as the holographic principle requires, then that horizon must be a highly chaotic, energetic place. To an outside observer, the information is smeared across the surface, but to you, the astronaut falling in, quantum theory suggests that the particles just outside the horizon must be intricately entangled with particles radiating away as Hawking radiation. For the information to be preserved, this entanglement is crucial. Yet, for you to have a no-drama crossing, those same particles must also be entangled with particles inside the black hole. A fundamental rule of quantum mechanics states that a particle cannot be maximally entangled with two different systems at once. This is monogamy of entanglement. So a choice must be made. Either the entanglement with the Hawking radiation is broken, which would destroy information and violate quantum law, or the entanglement with the interior is broken. If the link to the interior is severed, the calm space at the horizon vanishes. In its place, the astronaut would encounter a searing wall of ultra-high-energy particles, a literal firewall that would instantly incinerate anything crossing it. This is the paradox. The holographic principle demands information preservation on the horizon, but that very demand seems to replace the horizon with a deadly barrier, violating Einstein's bedrock principle of no drama. The firewall is not necessarily a prediction, but a glaring signal that our current understanding is incomplete. It forces physicists to make a brutal choice between three cherished pillars: quantum mechanics, general relativity, or the holographic principle's version of information conservation. They cannot all be perfectly true as we currently understand them. This conflict is pushing theorists to radically rethink the nature of locality, the idea that objects are only directly influenced by their immediate surroundings. In a holographic universe, locality might be an illusion that breaks down spectacularly at the horizon. The entanglement that weaves space itself together in the bulk might have a more complex, non-local description on the boundary. Solving the firewall paradox likely requires a new understanding of how quantum entanglement builds the very geometry of spacetime, suggesting that space is not a static stage but a dynamic network of quantum connections. The firewall shows us that the holographic principle is not a finished answer. It is a powerful, disruptive tool, actively breaking our old intuitions to force a deeper theory of reality into view. The terrifying paradox of the black hole firewall reveals a desperate need for a new language, one that can seamlessly weave quantum mechanics and gravity together. This is where string theory enters the stage, not as a distant relative, but as the very mathematical arena where the holographic principle was born and proved. The groundbreaking AD-SCFT correspondence, that perfect duality between a gravity-filled bulk and a quantum boundary, was not a philosophical guess. It was a concrete discovery made by physicists working deep within the equations of string theory. To understand why, we need to see what string theory actually proposes. For decades, physicists have struggled with the fact that quantum theory, which rules the very small, and general relativity, which rules the very large, are mathematically incompatible. String theory offers a radical fix. It suggests that the fundamental building blocks of nature are not zero-dimensional points like dots on a page, but incredibly tiny, vibrating one-dimensional strings. Just as a single violin string can vibrate at different frequencies to produce distinct musical notes, these cosmic strings vibrate in different patterns. One vibration might manifest as an electron, another as a quark, and another as a photon, the particle of light. In this elegant vision, all particles and forces are unified as different musical tones played on these elementary strings. But this beautiful idea comes with a startling requirement. For the mathematical symphony of string theory to be consistent, to avoid fatal errors, the strings cannot vibrate only in the three spatial dimensions we know. They require extra dimensions of space, often 6 or 7 more, curled up into shapes so tiny we could never perceive them directly. This is the crucial link to holography. These extra dimensions provide the expanded stage, the higher dimensional bulk necessary for the duality to work. In the AD-SCFT model, the 5-dimensional universe with gravity is a specific solution within string theory. The strings vibrating in that bulk space with all its extra dimensions create the particles and forces we would see. And the miraculous mathematical proof showed that this entire complicated stringy construction is exactly equivalent to a simpler, ordinary quantum field theory living on its 4-dimensional boundary where the strings and the extra dimensions are not present. Think of it like this: string theory provides the detailed blueprints for a magnificent, multi-leveled palace. The holographic principle then reveals that this entire palace can be perfectly represented by a single, intricate fresco painted on its outer wall. The fresco is the boundary theory, and the palace with all its rooms and corridors is the stringy bulk. It is important to clarify, however, that while the holographic principle was discovered and solidified within string theory, the concept itself is broader. It is a profound framework about information, space, and emergence. In principle, other theories of quantum gravity might also realize a holographic duality. But string theory, with its inherent need for extra dimensions, provided the first complete and calculable example, turning a wild speculation into a rigorous tool. It gave physicists a working model of a holographic universe, a sandbox where they could test the limits of reality and discover puzzles like the firewall. So string theory is not just a candidate for a theory of everything. It is the foundational language that allowed us to read the first few pages of the holographic cosmic code, suggesting that the universe's deepest secrets are written not in the volume of space, but on its skin, in the vibrations of strings we may never directly see. The strings of string theory provide the mathematics, but what is the physical thread that actually stitches the projected reality together? The answer appears to lie in the strangest phenomenon in all of quantum physics: entanglement. When two particles become entangled, they lose their individual identities. Their properties, like spin or polarization, are linked in a perfect, instantaneous correlation, no matter how far apart they fly. Measure one, and you instantly know the state of the other. Einstein famously called this spooky action at a distance, a troubling violation of locality that seemed to suggest information traveled faster than light. But in the holographic view, this spookiness is not a bug, it is the fundamental feature. It is the glue. A revolutionary idea called the ER equals EPR conjecture makes this breathtakingly concrete. Proposed by physicists Juan Maldacena and Leonard Susskind, it suggests that quantum entanglement, the EPR part named for Einstein and his colleagues, is physically connected by the fabric of spacetime itself. More precisely, every entangled pair of particles is linked by a microscopic wormhole known as an Einstein-Rosen bridge or ER bridge. This is not a wormhole you could travel through. It is an unimaginably tiny, transient tunnel in the geometry of space. The conjecture boldly states that entanglement and these microscopic wormholes are two descriptions of the same thing. Where there is quantum connection, there is a geometric thread. Now scale this idea up to the holographic cosmos. Remember the quantum particles living on the two-dimensional boundary, the ones whose interactions project our three-dimensional reality. According to this view, those particles are not isolated. They are entangled with each other in an impossibly complex, dense web of quantum links. And each of those informational links, each thread of entanglement, corresponds to a tiny bridge, a stitch in the emerging fabric of spacetime. Imagine a vast cosmic loom. The individual threads, the entangled quantum bits on the boundary, are seemingly separate, but as the loom weaves them together, crossing and connecting, an image emerges. The flat tapestry that appears is not a new substance added to the threads. It is a direct result of their interconnection. In the holographic universe, the three-dimensional world with its hills, valleys, and gravitational wells is that tapestry. It is not built out of some ethereal spacetime stuff. It is woven from quantum entanglement. The smooth, continuous space you move through is an illusion created by the density of the weave. This turns our understanding of the cosmos inside out. We have always thought of space as the container that allows objects to interact, but here the interactions, the quantum entanglements, come first. They are the primary reality, and space is what emerges when there are enough of them. The force of gravity is not pulling objects across a pre-existing stage. It is a manifestation of the changing pattern of entanglement in the underlying quantum code. When a star warps the space around it, it is not bending a thing. It is altering the entanglement relationships between the boundary bits that project that region of space. So the next time you feel the solid ground beneath your feet or watch the moon trace its path across the sky, consider this. You are not standing in a container, you are standing on a picture. And the canvas holding that picture together is a silent, spooky, quantum conversation happening at the edge of everything. A conversation whose language is connection and whose poetry is the universe itself. This cosmic loom of quantum entanglement leads us to a different, yet strangely familiar idea. Many people, upon hearing the holographic principle, immediately think of the simulation hypothesis, the popular notion that our universe is an artificial construct, a sophisticated computer program run by some advanced civilization. While these two concepts can feel like philosophical cousins, they are fundamentally different in a crucial way. The holographic principle is not science fiction. It is a serious physical theory grounded in the established laws of quantum mechanics and gravity, born from solving concrete paradoxes like black hole information loss. It proposes that our three-dimensional reality is a projection from a two-dimensional surface, but that surface and the information on it are still part of the natural, physical cosmos. No programmer is required, no alien supercomputer is running the code. The universe, in this view, is simply structured like a hologram with its deepest description written on its boundary. The simulation hypothesis, by contrast, is a philosophical or metaphysical argument. It suggests our reality is an artificial creation, a simulated environment built by beings in a more fundamental, base reality. It often draws on trends in computing power and video game technology, asking if a future civilization could create a simulation so perfect its inhabitants would believe it was real. The key distinction is one of origin. Holography asks how nature itself is built. Simulation asks who might have built it, yet, for all their differences, they share a profound and unsettling overlap. Both ideas challenge the bedrock assumption that our sensory experience is the primary, fundamental layer of existence. Whether projected from a cosmological boundary or rendered on some cosmic graphics card, both suggest the world we perceive, with all its solidity and sensation, is a kind of representation. The ground beneath your feet, the warmth of sunlight, the vastness of the night sky, all might be the output of a deeper process, a more basic reality operating by rules we can barely glimpse. This shared implication is why both ideas resonate so deeply. They touch on ancient philosophical questions about the nature of reality and illusion, now dressed in the language of modern physics and technology. Understanding the holographic principle does not prove we are in a simulation, but it does something perhaps more powerful. It shows that our best scientific theories are leading us toward a universe where the line between what is real and what is emergent is blurring on its own, without the need for any outside programmer. The cosmos may be its own simulation, running on the fundamental hardware of quantum information, projecting the magnificent illusion we call home. These cosmic ideas of projection and entanglement are not confined to black holes or distant horizons. They are now being brought down to Earth, into laboratories where scientists are building tiny, artificial universes to test them. This is the new frontier of experimental holography, where the mind-bending mathematics of the AD-SCFT correspondence is being translated into real, physical systems we can control and measure. The goal is not to create a miniature cosmos with stars and planets, but to engineer a system of particles that perfectly mimics the mathematical relationships of a holographic duality. If they can build a quantum system that acts as the boundary theory, they should be able to observe the emergence of gravitational-like behavior in its collective properties, a shadow of the projection right here on the bench top. One of the most promising arenas for this work is in the realm of ultra-cold atoms. Using lasers and magnetic fields, physicists can trap clouds of atoms and cool them to temperatures just a whisper above absolute zero. At these frigid extremes, quantum effects dominate, and the entire cloud can behave as a single quantum object, a Bose-Einstein condensate. By carefully tuning the interactions between these atoms, researchers can create a quantum system that is mathematically analogous to the conformal field theory, the CFT, on the boundary of a holographic universe. They can then probe this system, looking for signatures that its collective behavior corresponds to phenomena we associate with gravity and curved space in the higher dimensional bulk. For instance, by introducing a controlled disturbance like a sudden change in the magnetic trap, they can create ripples that act like particles moving in an emergent curved geometry. They can search for analogs of Hawking radiation by creating an artificial event horizon within the fluid of cold atoms. Imagine a flowing river of this quantum fluid. If you make one region flow faster than the speed of sound for the waves in that fluid, any ripples trying to swim upstream against the current become trapped, just like light trapped behind a black hole's event horizon. At that artificial horizon, theory predicts the spontaneous creation of entangled particle pairs, a direct analog of the Hawking radiation that evaporates black holes. In recent years, several experiments have reported detecting exactly this kind of thermal glow from such analog horizons, providing tangible, experimental support for the underlying quantum processes that Stephen Hawking first described. Other labs are using different platforms, like arrays of superconducting circuits or ions suspended in electric fields. These systems act as perfectly controllable quantum bits or qubits, allowing scientists to precisely engineer the web of entanglement between them. By arranging these qubits in a specific pattern and coding their interactions to match the boundary theory, they aim to watch as geometry and even something resembling gravity spontaneously arise from the quantum connections. It is like teaching the threads on the cosmic loom a specific dance and then observing the pattern that appears in the woven fabric. These experiments are not proving our universe is a hologram, but they are doing something equally vital. They are stress testing the mathematical framework of holography in a real-world setting. They are asking, if the principle is true, what specific, observable consequences should we see in any system that obeys its rules? By finding those signatures in a jar of atoms or a chip of superconducting material, they build confidence that the mathematics is sound and points toward a real aspect of nature. This transforms the holographic principle from a speculative theory about the cosmos into a driving force for cutting-edge quantum physics, a new lens through which to understand how complex phenomena, from turbulence to high-temperature superconductivity, might emerge from simple underlying rules. The universe may be the ultimate hologram, but we are learning to read its code in the glow of a laser-cooled cloud right here at home. The glow of a laser-cooled cloud reveals a pattern, but where does that pattern become a thought? This leads us to a speculative yet utterly fascinating leap from the cosmos to the confines of our own skulls. A separate and highly controversial idea suggests the brain itself might operate on holographic principles. This is not the cosmological holographic principle of black holes and string theory, but a neurological hypothesis with its own history. It was most famously proposed by neuroscientist Carl Pribram, who was puzzled by the brain's mysterious resilience. You can remove large portions of a holographic film, and the entire image remains, just with reduced clarity. Pribram saw a parallel in the brain where memories are not stored in one specific location, like a file in a drawer. Even after significant damage or trauma, memories often persist in a degraded but distributed form. This suggested to him that the brain might encode information in a way similar to a hologram, using wave interference patterns spread across the entire neural network. When you remember your first day of school, that recollection is not pulled from a single neuron. It is reconstructed from a symphony of firing patterns across your cortex, much like a three-dimensional holographic image is reconstructed from the interference fringes on a two-dimensional plate. The brain's incredible ability for pattern recognition, for seeing a friend's face in a crowd from just a partial glimpse, also feels holographic. A small fragment of the interference pattern can still summon the whole image. Now, it is crucial to understand this is a metaphor, a powerful analogy, not established physical law. There is no proven quantum holographic film inside our heads, and most mainstream neuroscientists view Pribram's specific model as an intriguing but unproven speculation from a different era of brain science. Yet, the persistence of this idea in popular culture and some corners of theoretical biology is telling. It shows the immense reach of the holographic concept as a framework for thinking about information, wholeness, and emergence. Whether applied to the fabric of space-time or the fabric of consciousness, the hologram offers a compelling picture, a reality where the whole is contained in every part, and where what we perceive is a magnificent reconstruction from a deeper, coded surface. It is a reminder that sometimes the most powerful ideas in science ripple far beyond their original equations, inviting us to see connections in the most unexpected places. But for all its elegance, the holographic principle faces fierce and legitimate criticism from within the scientific community itself. The most potent critique centers on the very mathematics that gave it life. The AD-SCFT correspondence is a towering achievement, but it is a precise duality for a universe that is not our own. Anti-de Sitter space is a static, negatively curved cosmos with a clear, accessible boundary. Our universe is expanding, accelerating, and geometrically flat. Many physicists argue that until a similarly rigorous duality is found for de Sitter space, the holographic principle remains a brilliant solution in search of the right problem. It is a powerful mathematical tool, they say, but not necessarily a true description of physical reality. They see it as a fascinating property of a specific, idealized model, not a universal law of nature. This leads to a second major criticism, the lack of a smoking gun. While experiments with cold atoms and analog horizons are suggestive, they are precisely that, analogies. They show that systems can behave in ways predicted by holographic math, but they do not prove our specific cosmos is structured that way. There is no direct, universally accepted observation from telescopes or particle colliders that confirms we are living in a projection. The controversial statistical anomalies in the cosmic microwave background have not been confirmed, and other explanations exist. For critics, this absence of definitive proof is telling. They worry the principle has been overhyped, its profound implications leaping ahead of solid empirical grounding. It risks becoming a captivating metaphor that absorbs too much explanatory weight, a modern echo of the ancient idea of the universe as an illusion, now dressed in the formidable language of string theory and quantum information. These criticisms are not dismissals, they are essential to the scientific process. They force proponents to sharpen their ideas, to search harder for that de sitter proof, and to devise clearer experimental tests. The debate is alive and vigorous, a sign that the holographic principle is not settled dogma, but a living, breathing frontier of human curiosity. It stands at a precipice, balanced between being one of the deepest insights into the nature of reality we have ever stumbled upon, and being a beautiful, intricate mirage in the desert of theoretical physics. The journey to find out which it truly is may be just beginning. That fierce scientific debate over proof and reality is precisely why the holographic principle has exploded far beyond the pages of physics journals. It has become a cultural phenomenon, a story we tell ourselves about the universe that feels as much like myth as it does like math. You can see its fingerprints everywhere in popular culture, often long before most people had ever heard the term. The most obvious example is, of course, the film The Matrix. While it explicitly uses the language of computer simulation, its central premise is pure holographic intuition. The idea that the solid, tactile world of skyscrapers and spoons is a convincing data stream projected onto our senses, with a truer, more fundamental reality operating behind the scenes, captures the emotional core of the physics perfectly. It is not a documentary about anti-de sitter space, but it is a powerful dramatization of the feeling that our reality might be a representation. This theme echoes through countless other stories. In Christopher Nolan's film Inception, the layered dreamscapes are nested realities, each one feeling utterly real to those within it, yet all projected from a simpler, waking world. Television shows like Devs and Westworld grapple with the nature of programmed realities and emergent consciousness, questions that feel urgent precisely because science is now hinting that our own universe might be built on similar informational foundations. Even in literature, from the classic allegory of Plato's cave to modern science fiction, the archetype of a projected reality is a persistent and haunting one. The holographic principle gives this ancient philosophical fear or hope a new vocabulary grounded in black hole thermodynamics and quantum bits. It provides a scientific scaffold for a timeless human question: are we living in the real world, or are we shadows on a wall? This crossover into philosophy and spirituality is where the idea finds its deepest public resonance. For some, it feels like a validation of spiritual or mystical traditions that have long spoken of reality as Maya or illusion. It creates a strange and compelling dialogue between the cold equations of entropy and the warm, intuitive sense that there is more to existence than meets the eye. The principle does not prove any spiritual claim, of course, but it makes the conversation feel less fanciful. When a physicist at a prestigious university uses terms like projection and emergent illusion to describe spacetime itself, it legitimizes a broader cultural wondering. This is the unique power of the holographic principle. While the details of string theory or quantum field theory remain locked away in complex mathematics, the core idea is almost instantly graspable on an intuitive level. Anyone can understand the concept of a hologram, a three-dimensional image born from a two-dimensional surface. That simple, powerful metaphor becomes a gateway. It allows people to engage with one of the most profound and cutting-edge ideas in science without needing a doctorate to follow along. They might not calculate the Bekenstein bound, but they can feel its implications. This public engagement is not a side effect, it is a testament to the theory's raw explanatory power. It touches something fundamental in the human experience, our perpetual curiosity about the nature of the stage upon which our lives play out. In a world saturated with digital simulations and virtual realities, the question no longer feels purely abstract. It feels imminent, personal. The holographic principle suggests that the universe itself might be the original and most profound virtual reality, running on the oldest processor in existence, the quantum code of creation. And in that suggestion, physics, philosophy, and pop culture find a rare and thrilling common ground, all staring up at the same projected sky and asking, what is really on the other side of the screen? That cultural resonance points toward a deeper scientific ambition. The holographic principle is not just a fascinating idea about black holes. It is now a leading pathway in the most important quest in all of physics, the search for a theory of quantum gravity. For over a century, we have lived with a divided cosmos. General relativity gives us a magnificent picture of the large, describing how mass and energy warp the stage of spacetime itself, governing planets, stars, and galaxies. Quantum mechanics gives us an equally magnificent, yet utterly bizarre, picture of the small, describing a probabilistic world of particles and forces. The problem is, these two theories are written in different mathematical languages, and they violently disagree when forced to meet. At the center of a black hole, at the very first instant of the Big Bang, the universe was both incredibly small and unimaginably dense. Here, the smooth geometric curves of relativity shatter against the chaotic uncertainty of the quantum world. Our equations break down, producing nonsense answers of infinite density, singularities where physics as we know it simply ends. This is the wall we have hit. To move forward, we need a new framework that seamlessly blends the two, a single set of rules for the cosmos at every scale. This is the dream of a theory of quantum gravity, and increasingly, the holographic principle is seen not as a side note but as the blueprint. Its great power is that it does not try to force quantum mechanics into the mold of spacetime. Instead, it suggests that spacetime itself, along with the gravity that shapes it, emerges from a more fundamental quantum reality. In the holographic view, the quantum theory on the boundary is the complete description. The gravity and the curved geometry in the bulk are not separate things to be unified. They are the consequences, the projected image. This flips the entire problem on its head. We are no longer asking how gravity behaves quantum mechanically. We are asking how a specific, well-defined quantum system gives rise to the illusion of gravity and space. This approach has already shown incredible promise in taming the most terrifying places in the universe. Take the birth of the cosmos. The standard Big Bang model points to a singularity, a moment of infinite density where time itself begins. This is a clear signal that our physics is incomplete. Some holographic models offer a radically different origin story. They propose that our expanding, three-dimensional universe could have emerged from a quantum phase transition on a two-dimensional surface, like a three-dimensional image materializing from a flat plate. In this picture, the Big Bang is not a singularity in space, but a moment of transformation in the underlying quantum information. Time and space as we know them crystallize from a more primitive, timeless state of quantum entanglement on the boundary. Similarly, the terrifying singularity at the heart of a black hole, where relativity predicts the destruction of all known laws, might also be resolved. The holographic principle tells us the true description of the black hole is not a point of infinite density, but the complex, chaotic quantum state on its event horizon. The interior we picture all the way to its center is a projection from that data. There may be no singular point at all in the fundamental theory, only a supremely dense and complex arrangement of quantum information that our classical perspective misinterprets as a geometric catastrophe. This is why the principle is so compelling to those seeking a theory of everything. It provides a concrete framework where the two great pillars of modern physics are not forced to marry, but where one gives birth to the other. Gravity is not quantized, it is synthesized. The search is far from over. Finding the precise holographic description for our specific, accelerating universe remains the monumental task. But the path is now illuminated. Each step in understanding how quantum bits entangle to weave the fabric of space is a step toward the ultimate goal, a single, elegant theory that can describe the fiery birth of the cosmos. the dark silence inside a black hole, and the quiet reality of this very moment, all as different verses in the same quantum song. But the holographic principle is not the only contender in this grand quest. A very different vision of quantum gravity has been taking shape for decades, one that does not seek to project space from a boundary, but to build it from the ground up. This is loop quantum gravity, a framework that asks what happens if you take Einstein's geometric universe and apply the rules of quantum mechanics directly to the fabric of spacetime itself. Instead of spacetime being an emergent illusion, loop quantum gravity proposes it is fundamental but grainy. It quantizes geometry. In this picture, space is not a smooth continuum. It is woven from a network of incredibly tiny, one-dimensional loops like an unimaginably fine mesh. These loops and the knots and links where they intersect carry discrete units of area and volume. There is a smallest possible area, a smallest possible volume, a true atom of space. You cannot divide a patch of space smaller than this fundamental quantum, just as you cannot have half an electron. This creates a universe that is literally pixelated, but from the inside out, not projected from a distant screen. The dynamics of this evolving spin network, as it is called, gives rise to the familiar smooth geometry we experience on large scales, much like a digital photograph looks continuous from a distance. The contrast with holography is stark. Holography says spacetime is a collective consequence of quantum information on a boundary. Loop quantum gravity says spacetime is made of quantized geometric building blocks. One view is top-down, the other is bottom-up. They are competing philosophies encoded in mathematics, each trying to solve the same paradoxes of black holes and the Big Bang. And there are other fascinating players in this competition. Approaches like causal dynamical triangulations take a radically computational view, building spacetime from simple geometric blocks like triangles or tetrahedra that glue together following strict causal rules. By simulating the connections between trillions of these tiny building blocks, a large-scale, smooth four-dimensional universe can spontaneously emerge from the chaos, a powerful demonstration that our classical reality could be a statistical average of quantum geometric possibilities. This vibrant landscape of ideas is not a sign of confusion but of profound creativity. It shows that the deepest questions in physics are alive and fiercely debated. Scientists are not marching in lockstep toward a single answer. They are exploring multiple, wildly different paths through an unknown territory. The holographic principle, with its breathtaking vision of a projected cosmos, is one brilliant map. Loop quantum gravity, with its woven quantum space, is another. Their very disagreement is a beacon, illuminating how far we are from a final theory and how thrilling the journey of discovery truly is. The vibrant debate between competing theories of reality forces us to confront the most intimate question of all. If the holographic principle is correct and our flowing experience of time and choice is a projected story from a timeless, deterministic quantum code, then what becomes of free will? This is not a question physics can answer, but it is one the principle makes impossible to ignore. On one extreme lies the specter of hard determinism. If every event in our three-dimensional world, every neuron firing in your brain, every decision you make, is the exact predetermined output of quantum data processing on a two-dimensional boundary, then the feeling of choice is the ultimate illusion. You are reading these words not because you chose to, but because the cosmic code written at the beginning of time dictated that this exact sequence of photons would hit your eyes and this specific cascade of thoughts would unfold in your mind. In this view, you are a character in a movie, believing you are improvising your lines while the film reel, the boundary data, has been complete since the moment of projection. Yet another interpretation, compatibilism, offers a more nuanced path. It argues that free will is not about being free from the laws of physics, but about being free from external coercion. Even if your decisions emerge from the deterministic or probabilistic dance of quantum bits, they are still your decisions, arising from the unique, complex configuration that is you. Your desires, your memories, your reasoning, all are part of that emergent projection. Choosing an apple over an orange is no less real because it corresponds to a specific state in the boundary quantum field. It is simply how choice manifests in a holographic universe. The will is not free from the system, it is a feature of the system. This philosophical deep dive becomes deeply personal when we consider consciousness itself. Is your subjective experience, the rich inner world of color, sound, and emotion, just another layer of the projection? Or could it be somehow linked to the fundamental quantum processing on the boundary, the true seat of awareness? We have no answers, only profound unease and wonder. The holographic principle does not rob life of meaning, but it reframes the stage. It suggests that the story of your life, with all its apparent twists and turns, is being written in two languages simultaneously: the language of cause and effect within the projection, and the language of quantum information on the edge of reality. Whether you call that fate, physics, or freedom may be the most personal interpretation of all. So where does that leave the sky above us? We began this journey with a single, poetic question. Is the sky a window, or is it a projection? After exploring black hole paradoxes, cosmic dualities, and the quantum threads of entanglement, we now have a possible answer, one that reshapes our place in the universe. If the holographic principle applies to our cosmos, then the night sky is not a window into an endless, independent void. It is a display, the most magnificent screen imaginable. Every star you see, every swirling galaxy, the vast dark emptiness between them, all of it is part of the show, a dynamic, evolving projection of information from a distant, lower-dimensional surface we may never directly perceive. This does not make the universe less real. The warmth of sunlight on your skin, the crushing gravity of a black hole, the expanding fabric of space itself, these are all undeniably real experiences within the projection. They obey consistent, discoverable laws. The holographic view simply suggests that reality is structured in a more profound and unexpected way. The solidity and separation we feel are emergent properties, like the wetness of water emerging from countless individual molecules. What is fundamental is not the stuff of space, but the relationships of information. The cosmos is not a container of things, but a conversation of quantum data. And what we see when we look up is the breathtaking visual representation of that ongoing computation. It is a reality built not from bottom-up construction, but from an inward-outward projection. So the next clear night, step outside and look up. The light from those ancient stars has traveled for millions of years to reach your eyes. In the old view, you are looking back in time across a vast, empty stage. In the holographic view, you are witnessing a real-time rendering of the universe's deepest code, a cosmic film where every photon is a pixel and the entire sky is the story it tells. The breathtaking view of the sky as a cosmic screen leaves us with a profound sense of awe, but also with a long list of unresolved puzzles. For all its power, the holographic principle is a framework filled with tantalizing mysteries, open questions that keep physicists awake at night, pushing the boundaries of what we can know. The first and most formidable of these is the de Sitter problem. We have a precise holographic map for a universe that is the geometric opposite of our own, a static, negatively curved space. But our reality is expanding and accelerating. How do we formulate an equally rigorous holographic description for this, our actual home? Finding the mathematical key to a de Sitter conformal field theory, correspondence, is perhaps the single greatest challenge in the field. It is like having a perfect translation guide for a language no one speaks, while the living, breathing language of our cosmos remains just out of reach. Without this key, we cannot say for certain that the principle applies to everything we see. Even if we crack that math, we need proof written in the sky itself. Can we find definitive observational evidence? Scientists are looking for faint holographic signatures in two places: The first is the cosmic microwave background, that ancient wall of light. Future space telescopes with even greater sensitivity will scan its subtle temperature variations for statistical anomalies, for a preferred direction or a limit to detail that betrays a pixelated canvas. The second frontier is gravitational waves, the ripples in spacetime itself. As observatories like LIGO and future space-based detectors listen to the collisions of black holes and neutron stars, they might hear subtle echoes or modifications to the signals, whispers of how spacetime behaves at its most fundamental holographic level. These are the experiments that could turn a beautiful theory into a description of our world. Then there is the mystery of time itself. In the holographic view, the boundary theory is often described as timeless or static. The quantum information is just there, like the data on a DVD. Yet our lived experience within the projection is one of relentless flow, of cause and effect, of past and future. How does the arrow of time, the feeling of moments passing, emerge from a timeless code? This is not just a technical problem, it cuts to the core of our existence. Is time the most convincing illusion of all, a narrative structure generated as the cosmic processor reads out the data? Or is it woven into the quantum entanglement on the boundary in a way we do not yet understand? Finally, we come to the ultimate question of substance. What is the exact microscopic structure of the boundary theory? We know it is a quantum system of unimaginable complexity, but what are its fundamental constituents? Are they strings, as the original discovery suggests, or something else entirely, like quantum bits in a vast, entangled network? Is it a single, unified theory or a mosaic of different descriptions? We are like detectives who have deduced that a magnificent painting must have been created by an artist, but we have no idea what kind of brushes or paints they used, or even what the artist looks like. Understanding this microscopic structure is the final step in moving from a metaphor to a complete theory of reality. These open questions are not failures, they are the frontiers of discovery. They humbly remind us that we are at the beginning of a revolution in understanding, not the end. The holographic principle has given us a new map, but vast territories on that map are still labeled "Here be dragons." The journey to fill them in, to find the proof, to understand the emergence of time, and to decode the ultimate language of the boundary is what drives science forward. It invites all of us to ponder the edges of knowledge, to look at the night sky and wonder not just what it is, but how it is written, and what profound secrets are still waiting, encoded in the darkness. The true power of this idea lies not in its strangeness, but in its utility. The holographic principle has given physicists a revolutionary new instrument, a Rosetta Stone for translating between two seemingly separate worlds of physics. This is the gauge-gravity duality, and it turns the mind-bending concept into a practical tool for discovery. For decades, certain problems in quantum field theory, the framework describing particles and forces, were mathematically monstrous, too complex to solve. Conversely, understanding the quantum behavior of gravity around objects like black holes was equally daunting. The holographic duality changed the game entirely. It showed that an impossibly difficult calculation about gravity in a warped five-dimensional space could be perfectly mapped onto a much more manageable calculation about quantum particles interacting on a four-dimensional surface without gravity. It is like being given a secret passageway, allowing researchers to bypass a mountain of complexity by walking through a simpler, parallel dimension of mathematics. This has led to genuine breakthroughs, providing fresh insights into the behavior of exotic states of matter, like quark-gluon plasmas created in particle colliders, and even offering new angles on the perennial mystery of high-temperature superconductivity. By studying the gravitational dual of a superconductor, physicists can glean clues about how electrons pair up and flow without resistance in our own world. The principle is not just a statement about what reality is, it is a computational engine for understanding how reality behaves. its potential reach extends from the theoretical to the profoundly practical. The deep insights it provides into quantum entanglement and emergence are precisely the insights needed to build the technologies of tomorrow. To create a functional quantum computer, we must learn to harness and control vast networks of entangled quantum bits, protecting them from the chaos of the outside world. The holographic principle, which suggests that space-time itself is woven from entanglement, offers a fundamentally new perspective on how complex quantum systems organize and maintain stability. It could provide the blueprints for more robust quantum error correction, the essential ingredient for a scalable quantum machine. Similarly, in material science, the quest is to design substances with unprecedented properties, from room temperature superconductors to new forms of insulation. These properties emerge from the collective dance of billions of atoms, a dance that holography can model in a radically simplified way. By simulating the gravitational dual of a desired material, scientists might one day predict its behavior before a single atom is arranged in a lab. This transforms the principle from a philosophical curiosity into a potential catalyst for technological revolution. It reminds us that the most profound questions about the universe are never just academic. Asking if the sky is a projection is not an escape from reality, but a deeper engagement with it, one that might ultimately teach us how to build a better world from the quantum code up. We have traveled from the edge of a black hole to the edge of reality itself. This journey began with a paradox, the terrifying prospect that information could vanish forever inside a cosmic tomb. That single puzzle led us to a staggering possibility that our three-dimensional world of stars, planets, and people might be a magnificent holographic projection from a two-dimensional surface at the boundary of everything. Along the way, we saw gravity transformed from a fundamental force into an emergent phenomenon, a side effect of quantum information processing on a distant screen. We encountered the idea that the universe has a finite resolution, a pixelated graininess hidden at the Planck scale, and that every event within our cosmos is a real-time rendering from a deeper, simpler code. The sky above us may not be a window into an endless void, but the most breathtaking display imaginable, a story written in light and shadow, projected from the quantum script of creation. Whether this principle ultimately proves true for our specific universe remains an open, thrilling question for science, but its power is undeniable. It has reshaped how we think about space, time, and information, turning philosophical wonder into mathematical precision and laboratory tests. It reminds us that our quest to understand reality is never just about mapping what we see, but about daring to ask what lies behind the image. So the next time you gaze at the stars, consider both possibilities. You may be looking across vast distances of space and time, or you may be looking at a cosmic projection, a reality woven from entanglement and emerging from the edge. Either way, the universe is far stranger, more interconnected, and more wonderful than our everyday senses suggest. Exploring these ideas doesn't just solve equations, it expands the very horizons of human imagination. What do you think? Is our reality a hologram? Share your thoughts in the comments below and subscribe to join us for more deep dives into the greatest mysteries of space.